Good evening, everyone. This is Boise State Physics First Friday Astronomy. My name is Heidi Wu. I am an astronomer and assistant professor in the physics department. Before we get started, I have a few announcements. Our next event is third Thursday Planetarium show, which will happen on April 15th. So if you haven't, please sign up. Sorry. So our next event is third Thursday Planetarium show, which will happen on April 15th. If you haven't, please sign up at boi.st/third Thursday. I have also put the sign up link in the YouTube chat. So our events continue in the summer, both First Friday lectures and third Thursday Planetarium shows. And here I'm going to show you the poster for our summer First Friday talks. So in May, we will have Professor Travis Longcore from UCLA. He will be talking about light pollution in the Central Idaho Dark Sky Reserve. And in June, we will have Dr. Yiquan Chen from Ohio State. And he gave us a tantalizing title, How Dark is the Universe? And in July, we are very lucky to have Dr. Steve Swanson, who many of you know is a NASA astronaut and also faculty at Boise State. And finally, in August, you will hear from me talking about my research on galaxy clusters, and they are the giants in the universe. And our talk, at least the first two, will still be in the virtual format, still 7:30 p.m. Mountain Time. And depending on the COVID situation, we might be able to do the last two in person, or please stay tuned. So these events are open to the public and donation support. We would very much appreciate if you will consider donate at give.boisestate.edu/astronomy. So back to today's lecture. If anytime you have any question, you can use the chat feature on YouTube. So as you can see that Brian has posted comments, and then I posted the link here, and feel free to ask your questions. But of course, you need to sign in to ask questions. And I will be relaying the question to our speaker. So today, I'm very excited to be introducing Dr. Amy Choi from the Ohio State University. Dr. Choi received her bachelor's degree from University of Chicago and PhD from University of California, Davis. She was a postdoc at University of Edinburgh in Scotland before joining Ohio State's Center of Cosmology and Astroparticle Physics. Dr. Choi is an expert in gravitational lensing, which she will tell us about. And she has used several of the largest telescopes in the world to conduct her research. And she has made an important contribution to many of the gravitational lensing experiments. In fact, it would be pretty difficult to find an experiment that Dr. Choi is not making great contributions to them. Dr. Choi is also a sought-after speaker and educator. And you can find her talks and recent TV interview here on YouTube. Please join me in welcoming Dr. Amy Choi.
Thank you, Heidi, and thank you everyone at Boise State Physics for the invitation. I'm really happy to be here. So today we're going to explore one main question, namely, what is the universe made of? And some related questions such as, how do we know this? And what are we currently learning about the history of the universe? And finally, what will future experiments tell us? And it turns out that the universe is primarily made up of two important components. One is called dark matter, and it has a gravitational force, which is an attractive force, and it pulls things together. And then the second is called dark energy, and it exerts a repulsive force that causes the universe to rapidly expand. And here on this slide, there's an image in which there's actually a lot that we can see. So these are all visuals that we're able to see with our own eyes. So this is actually the visible side of the universe. And I wanted to start with this because it's a snapshot of some of the cutting edge data that we've been obtaining from the last several years. And if you're familiar with local galaxies, you might recognize two galaxies here called NGC 470 and 474. So they're quite nearby relative to most of the galaxies that I study. And they were originally discovered by William Herschel about 230 years ago. And today I'll focus on the two mysterious dark aspects of the universe, dark matter and dark energy. And I'll also highlight a particular method that I use in my research, which is called gravitational lensing. And I hope by the end you'll get an insight as to how we can see the dark universe using cosmic lenses. First, before we start talking about the universe on the largest scales, let's take a step back and get a sense of scale and where we are within that. So most of you are probably in Boise. I'm in Columbus, Ohio. But on universe scales, we're really more or less in the same place because we're all on planet Earth, which is rotating around the sun. And then the sun and the planets comprise our solar system, which is located in the Milky Way galaxy. And the sun is just one of many, many stars, estimated on something like hundreds of billions of stars in the Milky Way. And we are about 25,000 light years from the center of the galaxy. And so that's something like 1.5 times 10 to the 17th miles. So again, that's 17 zeros, and the difference between Boise and Columbus is only 2,000 miles. So really it's very, very close. We're basically next door in terms of the galaxy. Okay, so we can think even bigger and think about where the Milky Way galaxy is located itself. So the Milky Way galaxy is part of what we call the local group, which consists of several gravitationally bound galaxies in kind of this group. And groups can also live in much bigger types of environments. So here, what's pictured is a galaxy cluster. And galaxy clusters can contain anything from tens to thousands of galaxies that are connected together by the gravitational force. And on even bigger scales, galaxies, we think they live in a giant cosmic web. And I'm using that word web because it's a description of the filamentary structure of how these galaxies would all appear when you really zoom out and look at everything on the largest scales. And we can take a look at a visualization of this from the Sloan Digital Sky Survey, which mapped about a third of the sky. And the astronomers involved with this survey took the information, the observations that they took of the galaxies, including positions and shapes, and something about the light being emitted from these galaxies, and they put them into this visualization. And so we're seeing this as as if we were flying through past all of these galaxies. And you can kind of get a sense that there are regions where there are lots of galaxies closely clustered together. And then there are also these very large regions of empty space. And so overall, it kind of gives a sense of this filamentary web and a sense of what the structures look like on really large scales. Okay, so the first thing I'd like to talk to you about is focus on dark matter. And a story about dark matter wouldn't be complete without mentioning Fritz Zwicky, who is a Swiss astronomer who was based in Pasadena at Caltech for most of his academic career. And in the 1930s, he was doing an analysis of this data on the left, pictured on the left. This is a picture of the nearby Coma galaxy cluster. And the colors are a little bit different than what we were looking at in previous images. So here, these kind of white, bright blue, blobby objects, these are the galaxies that are part of this galaxy cluster, and they're gravitationally bound together. So Zwicky conducted an analysis of the speeds of the galaxies traveling around in this galaxy cluster. And he found that the speeds were surprisingly fast for what he expected if the mass connected to these galaxies was purely associated with the light being emitted. So there was something not quite adding up about the expected mass and the relationship to the speed that these galaxies were traveling. And it seemed to be that, in fact, there had to be some additional mass that we couldn't see with our eyes that had to be present that exerted a gravitational force that caused the galaxies to travel as fast as he measured them to. So let's think about this from another perspective. And if we were to do a quick at-home physics demo, which I don't really have a ball and a string, but just imagine, for example, I'm swinging around a ball and a string. This is actually a fitness watch charger. But if I put a lot of force into it, I can make that ball and the string travel really fast. And then if I don't put very much force into it, it might slow down. And so this force that I'm exerting with my hand here is directly related to the force that this ball is feeling. The ball also has some sort of mass, and it's traveling in a speed that kind of circles the hand in some direct relationship. So the speed is really related to the force that's being applied. Now, if we make an analogy to what's happening in a typical galaxy, the galaxy is full of stars and it has a lot of mass, and the mass exerts the gravitational force. And so instead of the hand, we have the force of gravity, which comes from the mass of this galaxy. And instead of the ball on the string, you could have, say, the sun, instead of the ball, is traveling around at some speed that's related to the gravitational force that is in turn related to the mass of the galaxy. And so the more mass there is, the more gravity, and the faster stars like the sun will travel. And we think that there is a lot more mass present when we make measurements of the speeds of stars, so not the sun, but other stars traveling around nearby galaxies, we think that there's a lot more mass here than can be explained by the light that we can see with our eyes. And we think that dark matter is a good way of explaining how this comes about. And so dark matter is a type of matter that doesn't seem to emit, absorb, or reflect electromagnetic light, but does seem to have a gravitational force and can be detected that way. And we think that it surrounds galaxies. And so you can think of this picture as there's all this light that we can see with our eyes, but it's actually also surrounded by a massive halo of dark matter. An example of one of the most convincing pieces of evidence that dark matter exists is very much related to what I was just talking about. And this is a galaxy rotation curve. On the horizontal axis, the x-axis here, we have the distance from the center of the galaxy. And then on the y-axis, we have a speed. So these data points that are being measured here come from speeds that are measured from stars at different distances from the center of a nearby galaxy. And so these are the actual speeds. These data points with error bars are the actual measurements. And at some distance, so you can see even in this image, as you go out to the outskirts, as you travel far away from the center of that galaxy, you start to get much fewer stars. So it's harder to find stars to make measurements for. And so at that point, typically people turn to making measurements of gas using radio. And so those are the blue data points here, and we're able to continue out to quite large distances from the center of the galaxy. Now, if all the mass came from visible stars and gas, then this dashed line here is the prediction for what the speeds should be based on all the mass coming from stars and gas. Now, there's a huge difference between that prediction and the actual measurements, and that can be explained by dark matter. And then if you actually include dark matter in the prediction, you get this solid white line here, which seems to go through the data points very well. So this is an indication that dark matter can explain the very fast speeds that are measured. A scientist named Reuben and her collaborators pioneered these measurements in the 1970s. And so on the left, there's a picture of her at the Kitt Peak National Observatory in Arizona. And then on the right is one of the plots from one of her papers, where again, it's the distance from galaxy center on the horizontal axis, and then the speeds of the given object that was measured on the y-axis. And here, there's just a line. These are all measurements, but there's a line being drawn through them just for comparison of the trends. And for all of them, you can see that out to very large distances, they don't seem to taper off as we would have expected if there was no dark matter, but they seem to remain relatively flat. And so this, to me, is one of the most important pieces of evidence for dark matter. Okay, so if this talk had been in person, I'd pause at this point to find out what you think dark matter is. And I'd still like to take some moments to consider some options. So if you're on Zoom, you can use the chat feature also to express your opinion if you have a preference among these options. Or if you're on YouTube, you can also state a preference using the chat. So yeah, feel free to write what you think. I'm going to go through these 4 potential options. A is that they are dead or weakling stars that we can't see. And by this, I'm referring to objects such as black holes, neutron stars, and other objects that don't really emit or reflect much light. Option B is a new type of particle that hardly ever interacts with the stuff we're made of, but it still interacts gravitationally. Option C is, well, maybe we don't actually understand gravity, and that's why the math hasn't been working out so far. And D is some combination of the above. So again, you're welcome to drop your thoughts in the chat. So Heidi has said B. And it's true that most of my colleagues would probably choose B as the most likely answer because it seems to make the most overall sense and fit in with the observations in the clearest way. And then there's also, Brian says, we've also got some takers for C and D. And I'm glad to hear that, because also I have colleagues that would be a fan of C, because it is true that we haven't really tested gravity on the really largest scales as stringently. So for example, we do have a lot of very solid pieces of evidence that gravity works exactly the way we think it does, to very high precision. So experiments on Earth, and also shooting lasers at the moon. And so we know that it does seem to work very well, as Einstein's theory of relativity lays it out for us. But it is true that on the largest scales, there may be something that we haven't quite detected yet. And this is something we would like to test further with upcoming experiments. Okay, so perhaps it behaves differently to what we expect. And it could be some combination of the above. But we do think currently that even though A might contribute a very, very small amount, it can't really explain the total amount of mass that we see. Okay, so I'd like to now talk about gravitational lensing, which is a particular method I use in my research. And this is a picture of how that works. So if we imagine light traveling from a very distant galaxy, so we are here on the lower right-hand side on Earth, and there's a very distant galaxy that's emitting light, and the light rays are traveling to us. Now, assume that on its way to us, it's going to pass by a very massive object, let's say a cluster of galaxies. And this massive object has a lot of gravity. The gravity actually serves to change the path of the light of the photons coming from the more distant galaxy, and it distorts the way the image of the galaxy appears to us when we receive and observe the light at Earth. And you can see that in this image, space-time is kind of laid out as this piece of graph paper. So if you think of just a normal sheet of graph paper where there's nothing heavy sitting on it, it's just maybe empty space, then the lines on that sheet of graph paper just go on the normal, like if we look out here, they go on a normal straight line. And light is always going to travel along kind of the straight line from point A to point B. But what this galaxy cluster is doing is it has a lot of mass, and so it's weighing down space-time, or weighing down the sheet of graph paper. And so what actually happens to these lines that were originally straight like this is that space-time becomes curved. And so now the path from point A to point B is now following along a curved path. And so we see this as a distortion of the light. So it may be helpful also to see that from this image. And so this is the path of the light coming from the distant galaxy, passing by a galaxy cluster. And as we observe it on Earth, it kind of takes this very arc-like shape. And so I'll play it one more time in case you didn't catch it the first time. And so instead of this original galaxy shape, we get this curved shape. Now, so this is a tabletop experiment I can't do live for you because I've actually tried, but it doesn't work out very well over Zoom. But I'm going to try to demonstrate how we can get these weird distorted shapes in this tabletop setup. So let's say that we have a source, like a galaxy that's emitting some light. And so in this case, we're just going to use a candle. And we know what this flame looks like originally. So that's the original source. Now, if we take the stem of a wine glass and kind of look through it so that it's oriented, really directly aligned with that original source light, you can get the light to bend around the stem of the wine glass kind of in all directions so that it forms a circle. And this is actually something we see in the universe. And this is an example of what we call an Einstein ring. which we also call a version of strong gravitational lensing because it's strong enough that we can see the effects by eye. Now, the more ubiquitous case that we get in the universe is actually a small distortion. So instead of the wine glass stem being aligned perfectly with that light source, it's kind of a little bit off center. And so we don't get a perfect ring, but we do get a small distortion that causes that light to be stretched in a noticeable way. And this slight distortion might be an example of something we call weak lensing, because we actually don't know what the source looked like before. All we have is the image of the light that's received at Earth. And so it's actually hard to tell, well, is this distortion, was the galaxy that emitted that light already elliptical, or was there a little bit of gravity that caused it to look even more elliptical? So we have to do a statistical analysis in most cases in order to determine whether it's gravitational lensing. Okay, so I said that we can get images like that in the real world, and these are some examples. On the top left here, we have galaxies that are gravitationally lensed by a galaxy cluster that's in the foreground. So what's in the foreground here are these bright orange blobs. And these are actually closer to us than these images that you can see. There are some very dramatic arc-shaped images that kind of almost form sort of a circular pattern around the galaxy cluster. And so these are galaxies, background distant galaxies that are lensed by a foreground galaxy cluster on its way to us. And I should also mention these are images taken with the Hubble Space Telescope. So we get really excellent resolution with the Hubble Space Telescope. And on the lower right, we see an example of a galaxy lensed by another galaxy. This is actually a very rare case where we actually have two galaxies. So a galaxy that's being lensed by another galaxy, and then another one that's also being lensed. And that's why we actually have these sort of two sets of rings here. So these are examples of Einstein rings. And again, for comparison, some of these images are similar to what we saw with the stem of the wine glass. All right, so then how do we detect the dark matter using this technique? And on the left here, again, we have another schematic of how it works. In this scenario, the light is coming from these distant galaxies. Originally, just for the sake of demonstration, these galaxies are pretty circular. So they started out being very round. And then as they passed by some lenses in the foreground, so closer to us, with a lot of mass and a lot of gravity that caused space-time to have some curvature, then how we see these galaxies that were originally circular is stretched in some way. And so these are the images that we actually measure. And this is kind of looking at it now in a two-dimensional projection in this lower panel. So the idea here is that we can take images of a large region of the sky, so lots and lots of galaxies in the image. We then want to measure the shapes of the galaxy images, so exactly what these shapes look like, and the average alignment at a given sky location. And then we can turn the problem around and solve for the mass that exerted that gravitational force that then caused these galaxies to be the shapes that we measure. So that's kind of a broad summary of what we do. Okay, so this is an example of a map, of a dark matter map, which we have made using the lensing technique that I just described. And here, where there are bright spots, the really white spots, that's where we think that there's a lot of dark matter. And we can also take the galaxy images and sum up the light coming from them. So where are the actual galaxies located? And that's what this map is. So this map is made by just counting up all the galaxies that we detect in different regions of the sky. And again, these bright spots indicate where there are a lot of galaxies. And it's kind of nice to then flip between these two, so the dark matter in blue and then the galaxy light in pink. And in some cases, you could kind of see, maybe I do that one more time, like in this location, you can see there's a lot of dark matter here, or also here, a lot of dark matter and a lot of galaxies emitting light in that location. So there is definitely some connection between the light and the dark matter. If we look again, this is the same dark matter map, but in a different color scheme. But again, these bright spots mean that there's a lot of mass, we think there's a lot of mass present. If we go to those locations in the optical data, then it looks like these three panels. So in each of these very dense regions, where the regions where we think there's a lot of dark matter, in the optical images, there do indeed seem to be a lot of galaxies in those regions. And these are actually examples of clusters of galaxies. So there's also a lot of light from galaxies in those areas. Okay, so I'm not going to talk about this much, but it's important in talking about dark matter that we also talk about how we're trying to detect it on Earth. So we haven't detected it yet, but I did mention earlier that we think that there is some new particle that may have the desired properties to fit in to explain all of the observations that we are seeing. And one way that people are attempting to detect these particles is to use these big detectors deep underground. So this is, on the left is a picture of the Sanford underground research facility. This is in North Dakota. It's located in a former gold mine. And this in the middle, it's kind of a strange fisheye perspective. In the middle, this is a tank of water. And inside of that, there will be a detector, sort of like what's pictured on the lower right here. And I believe this picture on the top right is kind of this interior thing in this diagram. And the idea here is that the dark matter particles are kind of surrounding us. And we want to catch them. We want to see some evidence that they exist, that there's some signature that they leave. But there are also lots and lots of different types of signals coming from space. For example, we have these really high energy particles called cosmic rays, which are coming from different sources out in space. And those are not necessarily the same as the dark matter particles that we're trying to detect. So the reason that we go deep underground, and I should mention this mine is something like 1 mile below the surface. And that 1 mile gives a lot of shielding to prevent the other particles from entering this detector and having their signal be measured. And so this is an ongoing, this particular one is called the Luxe Zeppelin experiment. And this is, I believe, either taking data now or very soon to. I know that they were scheduled to come online in 2020, and I'm not sure how their schedule has changed due to the pandemic. But it is, I believe, pretty much constructed and very soon to be taking data. So it'll be great to see what their first results will be. Probably we won't hear about that for a little while, but certainly something to keep your eyes and ears open for. Okay, so I also want to talk about dark energy. So I've talked to you about dark matter, which has a gravitational attractive force and it pulls things in. But we also have evidence for a force that actually causes the universe to rapidly expand. And in 2011, the Nobel Prize in Physics went to dark energy, to these 3 principal investigators who were involved in two competing supernova teams, and supernovae are exploding stars. And they use these measurements to discover that not only, so we already knew that the universe was expanding for quite some time, but not only was it expanding, it seems to be expanding even faster and faster. And so it's undergoing an accelerated expansion. And as an analogy to understand that, it's sometimes helpful to think about street lights. So if we're looking at these lamps at different distances from us, there you can think about it as distant lights with the same power. Let's say that they have the same number of watts that they emit. So if they have the same actual brightness, the closer ones will look brighter than the ones that are further off in the distance. But if you know how much light it was supposed to emit, then you can figure out how far away they are. So with these supernovae, which are exploding stars, we think we understand the physics mechanism behind why they explode pretty well, which also means we understand, or we think we understand how much light that they're producing, or actually supposed to be producing. And that means that we can measure the distances to the galaxy that they exploded in. And if you compare that distance to something called the redshift, which is a measure of how much the universe has expanded since the light left the supernova, then you can actually measure the rate of expansion. And we're finding that it's an accelerated rate of expansion. It's also helpful to look at now the dark matter and the dark energy as components of what I'm going to call the cosmic pie. So this is a flowchart showing the overall components of the universe. And really only a small slice of the pie consists of atoms like protons and neutrons and what we're made of. And pretty large portion of the pie, so almost a quarter, is actually dark matter. And then we think that dark energy is the rest, more than 70% of the components of the universe. And so again, dark matter, this is matter that emits no light, but it does interact through gravity. And then the dark energy is some form of energy that expands the universe. And it's also nice to look at simulations that people have done that put in as ingredients dark matter and dark energy into a simulation of the evolution of the universe. So this Z that's counting down, it's taking us from very early times in the universe when the universe was very young, and then evolves the model in the simulation to see what the universe looks like as we get closer to present day. And so you can see that as time goes on, what started originally as a more diffuse looking set of particles, they are coalescing, they're kind of being drawn in and attracted and creating these big, very dense, probably lots of galaxy clusters in those very bright regions. And then there's also very big empty regions of space, and a lot of that is coming from the fact that the space is expanding as time goes on as well. All right, so you can see that again here, that here is a comparison between two different simulations. One on the left is what we call lambda CDM. So that stands for lambda, which is the shorthand for dark energy in this case, and then cold dark matter, and refers to the dark matter component. And on the left, we have both dark matter and dark energy. And I'll play that one more time. And on the right, we have only dark matter. So there's no dark energy on the right. And as the time evolves, as the universe evolves, we get slightly different they look somewhat similar, but there are some differences between the final snapshot on the left and then the final snapshot on the right. Okay, and then the last comment is that we think that the model on the left and the simulation on the left reproduces the observations that we measure in terms of positions of galaxies much better than the one on the right. And here's an example of a comparison between simulations and reality. And here it's kind of a projection now. So before we were looking at 3D spaces, and now this is projected onto 2 dimensions. But you can still see this filamentary structures. And this is another slide on which I would probably ask the audience, which one do you think is simulation, which one is reality? But I won't do that here. And also they are labeled. So you might, if you can read the labels, these 2 on the top and the left, these are taken from real data sets. So these reflect the positions of galaxies at different distances from us and at different regions of the sky. And then these 2 slices on the right and the bottom, these are coming from a simulation called the Millennium Simulation. And we've actually been able to tune the ingredients going into the simulation on the right and the bottom to such a degree that I think it's actually very hard to tell the difference between, so I think this one, the right and left are meant to kind of look like each other, and then the top and bottom are also meant to look like each other. And it's usually pretty hard for people to really tell the difference between simulations and data at this point. And now I'd like to tell you a little bit about the Dark Energy Survey. And this is a project that I've been working on for several years. And this is a picture of the actual telescope. It's based at the Cerro Tololo Inter-American Observatory in Chile. And because it's in Chile, you get a beautiful picture of the southern sky. And so you get these 2 objects here that we unfortunately cannot see in the Northern Hemisphere. But you might recognize that this is the large Magellanic Cloud on the left and the small Magellanic Cloud on the right. The Dark Energy Survey, the actual observations lasted about 5 years, well, 6 years. And it's an international collaboration over many countries, including the US, UK, Europe, Australia, Chile, Brazil. I might have forgotten one, but there, just to give you the idea that there are many people from institutions around the world, hundreds of scientists involved, including undergrads, grad students, postdocs, faculty, people who work at national labs. It's a very big operation. And the idea here is that we have 5,000 square degrees. So that's the area that it covers on the sky. And there are 5 optical filters, or 4 main optical filters that we're making measurements in. And this is the telescope again. It's called the Blanco Telescope. It's 4 meters in diameter. And the goal is to study both dark matter and dark energy with gravitational lensing and also other approaches. And here's a picture that's several years old now, but this was at a collaboration meeting at Chicago, I think I can't remember exactly, but it was several years ago. And so again, you can see that there are lots of collaborating institutions. This is a picture of the detector in the top right, and then also a person sitting here for scale. And here's the dome open. And during the pandemic, this is what we look like. So unable to meet in person, but last May, we did have a meeting virtually over Zoom. So this is the photo we took from that. And now we have made mass maps using gravitational lensing, using the techniques that I described earlier. And I might, let's see if I can oops. Okay, so I can't slow this down, but the idea is that the small region is an earlier version of the data set, and then the medium-sized region that was from a data release from some number of years ago. And this full map, that's what we recently have measured, and it's soon going to be published. Okay, so this large map, the largest one, was made from the analysis of over 100 million galaxies. And so we think that the blue regions in there, those are empty regions of space, and then the redder it is, the more dense or the more mass there is there. Okay, so one of my collaborators made this GIF, which I also enjoy. So again, you might ask, well, why does it have this shape? It kind of looks like a tank or maybe like a hummingbird. That has to do with the observing pattern, like the chosen area that the survey was taking observations on. And then this top region, it kind of sticks out like this because there was another data set that we wanted to overlap. Like we wanted to get data over the same region as another survey. And that survey happened to look like a long rectangle. And so it kind of adds this long thing at the top, which makes it look a little odd. But again, this is the mass map in slightly different colors overlaid on a particular projection of the full sky. And so the southern hemisphere, so the Milky Way plane is kind of distorted here due to the projection, but that's what this is. And then again, we're in the south. So here is the large Magellanic Cloud, and here's the small Magellanic Cloud. All right, so I'd like to take a few minutes to talk about the future experiments. And one of the telescopes that's currently being constructed now is the Verisi Reuben Observatory. So you might remember earlier I talked to you about how Reuben was really one of the pioneers of making measurements of galaxy rotation curves, which is one of the most robust pieces of evidence we have for dark matter. And so we've named this observatory after her. And again, this is her on the left here. And this would be an 8.4 meter telescope based in Chile, just pretty much on the next mountaintop over from where the dark energy survey was taken. And it will survey the entire available sky every few nights. And first light is expected soon. So there's a smaller camera that's being tested, which hopefully will turn on sometime this year and receive first light. But then there's also the bigger camera that will be put on to conduct a very long survey. So like a 10-year survey starting in hopefully 2023, known as the Legacy Survey of Space and Time, or LSST for short. And this is really going to tell us a lot about dark matter and dark energy. And there's a collaboration called the Dark Energy Science Collaboration, which is currently working together to figure out how best to run these analyses. And it's important to point out that this observatory will also find all kinds of visible matter too. So stars and galaxies. It's going to be probably revolutionary for astronomy, and something like 20 terabytes of data per night, because it's getting a lot of pictures of the sky. All right, so far I've been talking about ground-based imaging, but you did see some space-based imaging earlier from the Hubble Space Telescope. So ground-based imaging can have its issues. It can be very blurry due to the atmosphere. But if you go to space, you can really cleanly resolve each and every galaxy. And so you get a much more clear view like this. And actually, if you look carefully, and these images are taken from the Hubble Space Telescope. And if you look closely at the one in the center, there's an Einstein ring in there. And there are some space telescopes that are going to be launched, which we will be able to do further lensing analyses with. So Hubble is actually still taking data. So that's currently one of the important resources for these data. And further down the line, there is something that was originally called the Wide Field Infrared Survey Telescope, which was recently renamed for the first chief of astronomy in the Office of Space Science, whose name is Nancy Grace Reuben. And so this is a telescope which is basically the same size in terms of the telescope as Hubble, and same power, same resolution, but 100 times the field of view. So what that means is that instead of looking at very small regions of the sky at any one time, the field of view is actually 100 times the size of Hubble. And this picture on the lower left is an example of what the detectors on the Roman Space Telescope might be able to see. And this is a simulation. And the idea here, same as with the Reuben Observatory, is that we want to investigate dark energy and dark matter. We also want to look for planets outside of our solar system and look for exploding stars, supernovae, and really much more. And here's a picture on the right for the Harris Corp, which is making the kind of building the telescope assembly. All right, so I told you about Roman and Reuben, and from my standpoint, these are really the future for lensing. So again, the Reuben's legacy survey of space and time is going to image the whole sky every 3 nights and be really exciting. And then we also have, oh, I forgot to update the name, to the Roman Space Telescope, which is going to be operated by NASA, and that will be in space. And it's going to give us Hubble Space Telescope quality infrared images across many thousand degrees. So those are very exciting. So these are my conclusions. If you want to tell your friends what you learned tonight, on the one hand, we have the mysterious dark matter that we think surrounds our Milky Way galaxy and is present in the universe, and it stops the stars from flying apart because of the gravitational force. And then on the other hand, we also have this mysterious entity called dark energy, and it's causing the universe to rapidly expand. And our final understanding of the dark universe could maybe involve some new physics that will change the way, like what we know now about gravity, and it will change the way that we see the universe. And finally, I put some links here in case you want to learn more about the dark energy survey. So this is the one where we already have a lot of data that we're analyzing now. And there's some pretty cool things at the dark energy survey website. There's also a Facebook page and a Twitter page. And yeah, I forgot the Instagram page, but we're also on Instagram. So please do give a follow and stay tuned for all of the exciting new results that will come out with future experiments. So thank you.
Thank you so much, Amy. This is wonderful. So we got quite a number of questions so from the audience. So let's see. First one from the YouTube. I think this is related to the galaxy cluster lensing. The question is it possible to take spectra of the lensed galaxies to attempt to determine redshift for comparison to foreground cluster?
Yes, so that's actually important, and I didn't mention it so much because there's a whole body of research around the topic, but something else that's important in the lensing analysis, it's not just measuring the shapes of these galaxies, but also has to do with the distances involved. So the distance between us and, say, the galaxy cluster, and also the distance between us and the lensed galaxies. And so actually to solve for the dark matter that had to be there, we do actually need to know distances to all of these players in the scenario to a high level of precision. And so we do, in many cases, so taking spectra, so that's looking at the, getting the spectrum for the light coming from the distant galaxy, and using the spectrum, you can get a redshift. But it is actually very time consuming and expensive to obtain spectra for lots and lots of galaxies. And so we do kind of a rough version of that by using the photometry of the galaxies measured in different band passes. So there's different filters that you can look at the galaxy through. And we use those smaller number of data points, but it's really easy to get imaging of these galaxies as opposed to spectra. We use the imaging to estimate a redshift, and we call this the photometric redshift estimate. But the ultimate idea is to get an accurate understanding of what the redshift, what they are for those distant galaxies, and that is important.
Great. And another question, if we can't detect dark energy, how do we know it's 75% of everything? Is it just through redshift measurements? Yeah.
It's through a combination of different observations. So there's tons of types of observations that I didn't mention today that also measure the geometry of the universe in different ways. And lensing, for example, well, the supernovae are kind of one of the main ways of measuring the fact that we have dark energy. And so you can fit a model of like a model based on the physics, input physics, including different amounts of dark energy, and fit that to the observations of the supernovae. And we see that the fit is best when the number is around 75%. And it's similar with other types of measurements. So lensing is a little bit more indirect, although it does still say something about the geometry of the universe. But typically, the best way to constrain the 75% number is to combine different types of observations. And I didn't even mention there's something called the cosmic microwave background, which is the light emitted from the universe when it was very, very young. And those CMB, the cosmic microwave background photons, contain a lot of information that also help constrain this dark energy. And so there's just tons of different observations that together help us form this overall picture that 75% somehow seems to be the right number.
There's another question. So I think this question is related to the comparison between Sloan and then the simulation. So the question is that plotting the dark matter distribution or the distribution of visible matter?
So those, that simulation plot, that was the visible matter. So those are the locations of the galaxies that are detected. So actually using a spectroscopic survey, or two different spectroscopic surveys really. So for example, this one in the top, the Sloan Great Well, each dot on here represents the position, like the location of a galaxy that was measured in that survey. But we do think that there probably is also dark matter associated where that light is emitted.
Great. So Justin, you have a question. Would you like to unmute yourself and ask the question?
Sure, thank you. I was going to ask, because I think we'd actually discussed this a few weeks ago. Do we know if gravitational lensing extends like across the EM spectrum, like say outside of just visual and into infrared and or like ultraviolet? Thank you very much.
Yes, and thanks for the question. Yes, so we think it does. We actually make measurements of gravitational lensing even in, so like microwaves, and also the infrared. I'm actually not sure if I've ever seen a UV lensing analysis. It might be kind of hard to resolve things at the level that we would need to. UV measurements just happen to be a little bit harder to make in terms of, so I think the optimally, when you're really trying to resolve like how shapes are stretched out, optical and infrared tend to be the best bet for that, but you can actually measure lensing effects in these other parts of the visible spectrum.
Thank you very much.
Yeah.
Another question, are you also involved with DESI? And DESI is using a similar telescope as DES, but in the Northern Hemisphere. That's the question.
Yeah, so I'm actually not myself a member of DESI. So DESI stands for the Dark Energy Spectroscopic Instrument. And this is a spectroscopic survey. So related to what we were talking about earlier with obtaining spectra and exact redshifts, like 3D positions to distant galaxies. That's what DESI is going to do. But there are collaborators that I work with at the Ohio State University who are involved in DESI. So it's a pretty exciting project, which is they're working on getting the whole like the instrument running right now. Like they are taking data. They're trying to work on making things sure that things are working well. And then at some point, pretty soon, I think they're going to do what they call the 1% survey. So it's taking it's not like a super long survey, but it's kind of looking at some portion of what they want to eventually measure in order to kind of test their analyses.
Actually, just to advertise, our June speaker, Dr. Yiquan Cheng, is actually involved in DESI and also in spherics. I think there's a question about the NASA's spherics experiment. So stay tuned and you can ask Dr. Cheng about that in June. Okay, so another question. Do the new results at the LHC have implications in terms of what dark matter could be, ruling out certain theoretical particles, or too early to tell?
That's a good question. I'm afraid I'm not that up to date with what the latest results from the LHC. So also for others, LHC stands for Large Hadron Collider. And this is an experiment based in Geneva where they smash particles together and then they try to create new types of particles. And they're hoping, like that's another way of detecting dark matter potentially, is to smash particles at a high enough energy that dark matter particles are actually maybe created as a byproduct. So I'm not sure what it is that they have found that the question is referring to. But so far I know that at the LHC, as well as previous dark matter direct detection experiments, so far these experiments have kind of been ruling out the types of particles. So that's kind of what this question suggests. So ruling out certain theory particles and particular energies. But we haven't yet really gotten a smoking gun on like what is the actual particle that it really is. So yeah, I would guess that it's too early to tell, but I also haven't paid attention very recently to what they've come out with.
Great. And any more questions from people on the Zoom? I think all the questions on YouTube are answered. So and So thank you again so much, Amy, for this wonderful presentation. And and we got so many great questions, and your answers are really insightful. And we hope one day we will have the chance to invite you over to Boise so that you can actually answer more of our audience questions in person. And
thank you.
And thank you again. And thank you everyone on Zoom and on YouTube. And we'll see each other on Thursday.